Hi, everyone. Thanks for joining us this evening. Tonight, Yirou Chen is going to give us a tech talk on load balancers. Yirou, whenever you're ready, take it away.
Thank you, Ethan. Hi, everyone. My name is Yirou Chen. I'm very excited to talk to you today about load balancers. Before we get started, I would like to extend a special thank you to Co-Smith, Ginny, and Bracklett for being gracious in sponsoring today's tech talk. It is my hope that after today's tech talk, you can walk away and be familiar with load balancers, knowing what they do, why you should consider using them, and how you can go about potentially implementing them in your applications. So, what is a load balancer? Well, let's start with a scenario where you developed an application called My App, and you host it in your local machine, on your local machine. Well, in the first month, say you have 50 users sending requests to your server, which is a local machine at this point, on a daily basis. And your computer can somewhat handle those requests. But slowly, your app starts to gain traction and blows up. Now your computer no longer has the capacity to handle the exponential increase of traffic concurrently. And what is more, since you only have one server, and all the client requests are routed to this server, if your server ever goes down, which becomes the single point of failure, then you won't be able to fulfill any request until your server is up and running again. So in order to make your application more resilient, you decide to scale horizontally, which is by adding more machines. But then how do you decide which requests go to what server? And this is when a load balancer comes into play. A load balancer acts as the traffic cop, typically sits between the client and the server, accepting incoming network and application traffic, and distributing the traffic across multiple backend servers using various algorithms that we will get into later. A load balancer first ensures that the servers respond appropriately to requests, and then selects one from the set of healthy servers. If a server fails a health check, it's automatically removed from the server pool. And by balancing requests across multiple servers, a load balancer reduces individual load on the server and prevents anyone from becoming the single point of failure. We've just discussed the use case where we could place a load balancer between the user and the web server, which is a layer 4 load balancer. But we can actually add load balancers at 2 more places. First, we could add load balancers between the web servers and internal platform layers, which would be a layer 7 load balancer. And we could also add load balancers between internal platform layer and database, distributing queries across databases based on database load. At this point, you might be a little bit confused. Well, what is the layer 4 load balancer? And what is the layer 7 load balancer? Well, the layer 4 and layer 7 here are actually layers in the OSI model, which is also called an open system interconnection model. Simply put, it's essentially a reference system that lays out how computers communicate with each other over a network. So layer 4 here refers to the connection level. For layer 4 load balancing, we only know the client IP address and the ports, and we have no visibility to what the request data actually looks like. In this form of load balancing, all client requests are sent to the load balancer, which then distribute them to the appropriate backend servers based on the load balancing algorithm. So for instance, for a layer 4 load balancer, a load balancer with IP address of 2.2 receives data from clients with source IP address of 1.1. So the load balancer processes the request by changing the destination IP address to the designated server IP address, which is 3.3 here, and also changed the source IP address to the load balancer IP address itself. So during the whole network address translation process, only one TCP connection is made. Therefore, load balancing is actually very efficient and fast in this way, since there's no data lookup, and there's only one TCP connection between the destination and the source. And layer 7 refers to your application level. So application level protocols are such as HTTP or gRPC, and they run on top of TCP connection. For layer 7 load balancing, the load balancer can access the application data. So basically, you can look at, for instance, your HTTP headers and can be authorized to decrypt the data sent to the request. Therefore, the load balancer can look at the data sent from clients and make smart decisions on which server to be sent based on the data. This is great for microservice architecture, and caching can also be implemented here. So if we look at the diagram here, you can see there are a bunch of requests coming in to the layer 7 load balancer. And for instance, all the requests made to get JavaScript, HTML, and CSS files would be automatically directed to server 2. By now, I hope you're on board with ideas of using load balancers when building a robust and scalable application. Load balancers handle traffic spikes by moving data efficiently, optimizing application resource, and preventing server overloads. In addition, load balancers offer periodic health checks between the load balancer and servers to ensure they receive requests. The whole process mitigates the chance of any one server becoming a single point of failure, thus improving overall application availability and responsiveness. And here we're getting to the fun parts, load balancing algorithms. So there are two primary approaches to load balancing, static and dynamic. So dynamic load balancing uses algorithms that take into account the current state of each server and distribute traffic accordingly. Static load balancing, on the other hand, just distribute traffic without making those checks and adjustments. For static load balancing algorithms, we are going to touch on round robin, weighted round robin, and hash today. And for dynamic load balancing, we're going to discuss least connection, weighted least connection, and least response time. So what is round robin load balancing? Well, it's basically what it sounds like. So if we look at the diagram here, we have two servers. The first request goes to server 1, second goes to server 2, third goes to server 1, and fourth goes to server 2, and keeps rotating in that manner. So in round robin, requests from the clients are distributed in a cyclical manner, meaning the servers would take turns to receive requests. And what is weighted round robin load balancing? Well, it's essentially round robin, except that we take the capacity of each server into account. So say if server 1 can take 5 times the amount of load compared to server 2, then for every 5 requests distributed to server 1, we then distribute the next one to server 2, and we keep the rotation in that manner. Next, let's talk about hash load balancing algorithm. So the hash algorithm determines where to distribute the requests based on a designated hash key. It could be a client IP address, port number, or the request URL. So IP hash load balancing, for instance, uses source and destination IP address to generate a unique hash key and allocate the client to a particular server, which is what we just saw at the layer 4 load balancing slide. So if a session is broken, the hash key can be regenerated and the client request can be directed back to the same server as before. So IP hash load balancing is actually very useful when a failed connection needs to be returned to the same server. And there's also URL hash load balancing that generates a hash value based on the URL from client requests. So the load balancer caches the hash value of the URL. Any subsequent request to the same URL will result in a cache hit and forwarded to the same server. Well, this is very useful when you have a microservice architecture. So for example, if you're running a social media app, or the URL making requests to images, so like /images, could go to one server that just handles images. And all the other URLs, say user profile, /user likes, or such comments could go to another server that just handles user information. And lastly, we have random load balancing algorithm. So as this name implies, this algorithm matches clients and servers randomly, perhaps using an underlying random number generator. So in cases where the load balancer receives a large number of requests, a random algorithm will be able to distribute the requests evenly. So the random algorithm is actually very popular and sufficient for clusters consisting of servers with very similar configurations and when receiving a very large number of requests. Here we're at dynamic load balancing algorithms, where the load balancer takes into account the current state of each server and distribute traffic accordingly. There can be instances when, well, even if two servers in a cluster have exactly the same power and capacity, one server can still get overloaded a lot faster than the other one, just like an example here. So if you look at the diagram here, which is essentially round robin, right? Server 1 and server 2 both have 3 requests, but server 2 is overloaded since client 1 and 3 are disconnected from server 1, while client 246 are still connected to server 2. Well, in situations like this, the least connection algo would be a better solution. So the algorithm takes into account the number of active connections each server has. When the client tries to connect, the load balancer first try to figure out which server has the least number of connections, and then assign the new connection to that server. So if we use the example here, say if client 6 tries to connect after client 1 and 3 have already been disconnected, the load balancer sees that server 1 becomes the least connected server and would then assign client 6 to server 1 instead of server 2. And for weighted least connection load balancing, what it does to least connection algo is exactly what weighted round robin does to round robin. So we essentially factoring a weight components on the respective capacity of each server. So weighted least connections algo look at 2 things. First, the capacity of each server, and second, the current number of active connections on each server, and then decide which server to forward the next client request to. Lastly, let's talk about least response time load balancing. The least response time load balancing algorithm is just a more advanced version of the least connection method. So it forwards requests to the server with the least active connections, and then to the server with the least average response time. So if we look at the diagrams here, in the first diagram, server A has an average response time of 3 and has requests from client 1, 2, 3, 4. And server B has an average response time of 2 and has requests from client 5 and 6. So when there are requests coming in, the method first go look for a server that has the least active connection, which is server C right now, since it has 0 active connection. Therefore, in the second diagram, client 7 and 8 requests are directed to server C. And by this point, both server B and server C have 2 active connections. So where would the next request go? So basically, the load balancer checks and sees that, trying to find out which is the server that has the average least response time, which is server C. So then client 9 requests would then be routed to server C, and so forth. In summary, least response time load balancing first finds the server with the least active connections. And if there are multiple servers with the same least active connection, the load balancer finds the server with the shortest average response time and directs the request there. In conclusion, if you've never heard of load balancers, maybe you can walk away knowing some of the fundamentals today. And if you did have knowledge of load balancers, hopefully you've learned something new. And here are the resources I used to build this slide if you'd like to dive a little deeper. And here's my contact info if you'd like to connect in the future. Thank you very much. Have a good night.
Awesome talk, Yirou. Can everyone please unmute and give Yirou a round of applause? Good
Woo!
job.
Good job, Yirou.
Thank
Love
you.
Yirou.
Good job.
Good job.
Yeah.
Snuggled it.
Excellent. We don't have time for any questions. So with that, thanks again for joining us tonight. Have a great night, everybody.